Bismillahirrahmanirrahim. Today we will discuss properties of advanced materials, and under this topic, properties of advanced material, we will discuss optical properties. Assalamu alaikum. Today we are going to discuss the subject inorganic material chemistry. Course code is CAM 3115. Key concept that we will discuss under this topic, optical properties of advanced materials. First we will discuss about optical properties and its introduction. Then we will discuss the phenomena that involved in optical properties, about luminescence and types of luminescence, that may be fluorescence and phosphorescence. Then light interaction with solids, how light reacts with interact with solids or some medium. Then optical properties, examples of optical properties, in which we will take the example of from previous ancient times, and then we will take the example of gold and zinc oxide nanoparticles. Then we will discuss about quantum dots. So optical properties are actually, many of optical properties are closely related to the electrical and electronic properties of materials, but as we shall see, other factors also come into the picture when we are dealing with optical properties. When we talk about optical properties, so we can see that it is interaction of electromagnetic radiation with the matter. So by simply one can start with is by considering that a ray of an electromagnetic wave of single frequency entering a medium from vacuum. So this ray could be reflected when it enters the vacuum from medium. When it enters a medium from vacuum, then this ray or this light could be reflected, or it could be transmitted or refracted, or it could be absorbed. So there are three kinds of interaction. That could be reflection, that could be refraction or transmittance, or it could be absorption. For a more fundamental perspective, there are only two possibilities of interaction of a medium with electromagnetic radiation. There could be only scattering, or there could be absorption. So if someone consider a wider spectrum of frequencies, then some frequencies, some part of spectrum could be absorbed, while the other frequencies could be scattered. So there are two phenomena. There are two possibilities for interaction of light with the medium. Then there could be a scattering may occur, or there may be absorption of that light. As we previously talked about, that the light interaction with some medium or some solids. So this incident light could be reflected, it could be absorbed, or it could be transmitted. In this figure, you can see that the incident light, incident ray that strike a medium, when it enters the medium, then this incident ray is I naught, and when it is reflected back, it goes back to its angle will be same as incident light has. So it will be uh, represented by IR, that is reflected beam or reflected ray, and this one is that is in the medium, that is absorbed array, and this is IA, and that will cross the this solid, it will that will transmit from this solid, that will be transmitted ray, and that transmitted light that could be represented by IT. So if we say that photons of certain colors are absorbed, then they obviously are not being transmitted or reflected to your eyes. So this will affect the material color. So this interaction of light, if it is in the form of reflection, it is in the form of absorption, or it is in the form of transmittance or scattering, then it will affect the color of that material. So now looking luminescence, that is once radiation is absorbed, like you have incident radiation, and these are the energy level. And here you can see in the figure there are energy level, energy level in which the filled states are shown, and there are the empty states. And here you can see uh, filled orbitals, and other are empty orbitals, and in between filled and empty states there is a gap. So and that is known as energy gap. So if you shine or strike a light and there is an absorption of energy, that and then particles and electrons, these particles or electrons will absorb energy, and they will move from a filled state to the unfilled states. Filled states will be will have a lower energy. So when these particles electrons will absorb energy, then they will go to they will excite to higher energy states that are unfilled states. And this happens when light is absorbed. So now after some time, that electron which was in the higher energy level, that in higher energy level it will be unstable, and it can come back or relax back to the empty or to the field site which was created, to that hole where it was created. It will come back to the lower energy state which was created when the electron went up, and then it gives out radiation, and that is spontaneous emission. So you can have, in this case you can have absorption, and you can have emission when the electrons come back to field state. So it will either it will be in the form of absorption, or it will be in the form of that emission. Energy will lose in the form of emission. So what is the luminescence? A luminescence normally is that electrons which are excited, and when they take up some amount of energy, but the electrons which come back, like when we said that from lower state, that is filled state, when we strike a light, then these electrons absorb light and they become higher in energy. So when they will be in higher energy, they will go to excited state, they will go to higher energy state which is empty, and after some time they will come back to lower energy level. So at that time when they will come back, that electron will come back, then they may generate a different energy, and that may generate new photons by re-emission, and that is due to the fluorescence or phosphorescence. So in the luminescence, the radiated energy, that is the energy which is coming out, may or may not be equal to the energy being absorbed. Like if electron has absorbed energy and it go to higher state, and when it will come back, the energy that is released, it could be equal to the that energy which it absorbed, or it may be lower or higher than that of energy. So if it gives out the same energy which is absorbed, then it is just emission. But if that emitted light that has a lower energy, or that has a higher wavelength, then the energy of incoming beam, then our incident beam, then this is called fluorescent. And if it is delayed emission, like after some time it is you can get that energy, then that emission is called phosphorescence. So, and both these types of emission with lower energy of photons compared to the incoming photons is together called luminescence. So phosphorescence and fluorescence are both are the types of luminescence. Both together are called luminescence. So in luminescence, we can have phosphorescence, and we can have fluorescence. So fluorescence which can last for less than 1 second because it is very fast. And if this emission is our coming back energy emission is less than 1 second, then we can say it is fluorescence. But when it is delayed, that means it is very slow, then the emission is called that type of emission that mm, uh, when it is more than 1 second, then we can say it is phosphorescence, where the photon which is emitted is coming out after 1 second, like photon which is after when energy is absorbed, electron go to higher state, and when it come back, then it will emit. If it will come back in after 1 second, and it will be emit after 1 second, then it will call phosphorescence. And if it is it emits or it comes back in within 1 second or less than 1 second, then it is called fluorescence. So in phosphorescence, there is a delay between absorption and the re-emission, whereas in the fluorescence, it lasts only for very less time, less than, that is less than 1 second or within a second. So within a second, that emission or re-emission can take place. So typically, if you shine or strike UV light, that means your absorption is in the UV range. So emission may be in the UV, or it may not. It may be in the you shine UV, you will get blue emission. If it is you shine that blue or UV light, so you can get blue or you can get lower wavelengths. So if you shine blue light, then you would not get blue. It means it is if it is fluorescence or phosphorescence, then you will get red. That means a lower energy light will be emitted in luminescence. Now so if the luminescence ends rapidly, then the material is fluorescent, and because it luminescence only as long as it is excited, because the fluorescence is very fast. So then you will then because fluorescence is very fast, so if you switch on the light and the material is having absorption of energy, and it will fluorescence, and it will flow immediately, it will show or emit light. So if you remove that source of light, that fluorescence also will stop after switching off light. But in phosphorescence, what happens if you shine that or strike that material with that light, then after some time you stop the light. After stopping that light, it may also glow. So from that material, light will glow after when you switch off that light. So because this happens because it gives you a delayed radiation, that is after 1 second, so you can see its glow after when you switch off the light. So that glow or that energy is radiation is stored in that material. So that is called glow much after the light which was shining has been switched off. So if the luminescence continues and the material is phosphorescent, that means the light emission persists. That will differentiate it from fluorescent material. So these are the two important things about luminescence. So we can say that fluorescence and phosphorescence are two types of luminescence, and this luminescence is also known as photoluminescence if we are using light. So these are fluorescence and phosphorescence are two forms of photoluminescence or luminescence. So we can say that in luminescence or photoluminescence, substance glow is triggered by light. So both fluorescent and phosphorescence are based on the ability of substance to absorb light and emit light of longer wavelength. And if wavelength is longer, then energy will be lower than that of energy that is absorbed. So the main difference is the time in which it takes to do so. So we can differentiate phosphorescence and fluorescence by their time of emission or re-emission. So in fluorescence, we can say that emission is basically immediate. It could be within 1 second, and therefore generally only visible if the light source is continuously on. So like we are using UV lights, then if it is continuously on, then we can see emission in fluorescent material. While phosphorescent materials can store the absorbed light energy for some time, and they can release light later on. So which can result in an afterglow that can persist after the light has been switched off. So in case of phosphorescent material, that energy could be stored, and it could persist even you can switch off your light. So depending on the material, this afterglow can last anywhere from a few seconds to hours. So this in phosphorescent materials, this glow can last from seconds to hours. So if this light disappears immediately, then we can say that material is fluorescent, and that if that light will persist, then we can say it is phosphorescent material. So we can take the example of phosphorescent material. Like you can see that in many places you can see emergency exits that are a sign of phosphorescent materials. Nanoparticles show variation in color with change in the size of particles, and this is now a very established fact, and it has been very attractive. It is very attractive for students and scientists and practitioners, that scientists who are working in nanoscience and technology, and because a large number of interesting colors which can be generated with nanoparticles, and uh, people were making these nanoparticles very in earlier ages. For example, in left side figure, you can see it is a glass window, and this glass window was used in a famous church, and this which was very famous church, and all the glasses, these all glasses have window glasses have colors, and those colors were due to presence of gold nanoparticles, and because these windows were impregnated with gold nanoparticles. This thing we know now that these colors are due to gold nanoparticles, but at that time it was probably not known that why these colors appear in windows. So when it was made, so this was not known in early years, that when these windows were made, then people don't know that why these glass or windows show colors and what is the reason behind this. So but now after advancement of technology, we may know that these color is due to this color is due to the presence of very small gold nanoparticles. So presence of these cold small nanoparticles can show different colors. So in right side figure, you can see it is a picture of like Argosca that was made a very long time ago, and in about in 4th century AD. And this kind of cup was made where glass has been impregnated with gold nanoparticles, and this cup appears green in when light is reflected, and but it appears red when light is shown from inside. So that is transmitted through the glass, and which is transmitted through the glass. So This means that when the light is either inside or coming from other side, and in the reflected light, if you pass light on this direction, you observe the reflected light and then it looks green. And this is due to gold nanoparticles which are embedded in this glass. So these kind of structures were known thousands of years ago, and give you a reflection of what optical properties of nanostructure materials can be. And at that time it was people don't know that why this color green or red colors appears. So later on, by the discovery of electron transmission electron microscope, they observed that this cup has some mixture of gold and silver nanoparticles that are in the nanometer range, and they can reflect or transmit light, and they can show different colors. So today people are analyzing these kind of information, and this information is now being used in many applications. And this kind of information was present with us for centuries, but after analyzing, or after observing that this is due to the presence of gold nanoparticles, or this is presence of nanoparticles. So this is one particular application that you can have different glasses by using nanoparticles of gold with different sizes that can give you different colors. And today we have moved forward, and there have been many applications have been discovered and that are related to optical properties of nanoparticles. And these optical properties are being used in many applications in recent years. So later on, this was also analyzed that how this glass was made. So work suggested that glass containing minute amounts of gold and silver that have been prepared by heat treated, by using heat treatment, and by using different reducing agents, which produce collided metallic particles within the glass, and which results to color, because there are different colors of silver, and different sides of gold and silver are present. So these colors are actually produced in such a process, may depend on the concentration of that metals, or and the particle diameter that is present in that glass, and it is also dependent on the oxidation state of certain elements. Temperature and time also affect that the synthesis process, and the atmosphere in which that glass has been made. So this technology is now being used for the synthesis of gold nanoparticles or silver nanoparticles, and their optical properties are being analyzed, and that is being used in many applications. So here we will take the example of gold optical properties, and we will take example of gold. Like if we see bulk gold, like we use jewelry, and that the color of that gold is yellow, and but that is in bulk or micro, or we can say that in centimeter range or in micrometer range. But when we change the size of this gold, then the color will be different. Like if there are different sizes of nanoparticles, the color will vary according to its size. In this picture, you can see that bulk gold that looks yellow, but that gold colloids that are prepared in water, that was prepared by Faraday in 1856. And then the next picture is about latest synthesis of gold nanoparticles, that are gold colloids and nanoparticles that are synthesized in water. and this two solutions show red color, and here you can see the optical micrograph of 12 nanometer gold nanoparticles that also that look red. So it shows that if we use bulk gold, then color will look like yellow, but when we prepare its nanoparticles, that the color will be red, and this color could be other than red if we change the size of that nanoparticles. So these particles are so small that electrons are not free to move in as they can move in bulk. So they appear different. They show different colors. So because this movement is restricted in smaller particles, so particles react differently with light. So interaction of that uh, particles with light is different. So this interaction with light can show the different types of colors, different colors that could be due to the absorbance, reflection, or transmittance of that light. Similarly, if we take example of zinc oxide, then they also show some optical properties. If we will take here, we will take two types of zinc oxide nanoparticles, and we will compare them. So one is large zinc oxide particles that we can say these are bulk zinc oxide particles. So actually, zinc oxide nanoparticles particles have properties to block UV light, and they can scatter visible light, and so they appear white. If we in this picture you can see that this is uh, this emulsion is used in sunscreen, zinc oxide that would be used in sunscreen to block UV light. So in this picture you can see that this sunblock or sunscreen has been used on the face of this woman, and the color that you can see is a white, and this is white color appears for the large zinc oxide particles. But in case of nanosized zinc oxide particles can also block UV light, but they are small as compared to wavelength of visible light, so they cannot scatter the light. When they will not scatter the light, they will appear clear, so they will be transparent. So in the right side picture there you can see that emulsion is being used on hands, and this nanoscale or nanoparticle zinc oxide nanoparticles that are used in sunscreen, this color for emulsion is clear or it is transparent. So we can say that if we use larger particles or bulk particles of zinc oxide, and for the same compound, if we change the size of particles, the properties, optical properties will change. So the emulsion color will change here due to the presence of different sizes. So these zinc oxide nanoparticles could be used in these have their applications in sunscreen or sunblocks, which could block UV light, because we know that UV radiations are very dangerous, and they can cause skin cancer to humans or animals. So it is important to use sunblocks when we are going out or when we are exposing to radiation. So to prevent or block this UV radiations or UV light, we can use sunblocks, and in these sunblocks, zinc oxide particles could be used. In case of optical properties, quantum dots can produce different colors that are determined by the size of particles. That if different sizes will show different colors. So what are quantum dots? Actually, quantum dots are conducting nanocrystalline materials which have a diameter usually uh, between 2 to 10 nanometer, and here in figure you can see that there are quantum dots, that are many dots, and in right side figure you can see only one dot that showing close packed atoms inside in one atom. This is high resolution image, transmission electron microscope image, and left side is a low resolution transmission electron microscope image, which shows many dots in one image, and here we can see only one quantum dot that can show atoms inside it.
Quantum dots are tiny semiconductor crystals. This means that these particles can either conduct or resist electricity depending upon the temperature and purity of the semiconductor. Quantum dots range in size from 2 to 10 nanometers. Because of their diminutive size, the physics of these particles is governed by quantum mechanics. The size, energy levels, and emission color of quantum dots can be precisely controlled, which makes them extremely useful in a variety of applications. One of the unique properties of quantum dots is that their emission color depends on their size, not their material. The bigger the quantum dot, the larger the wavelength and the smaller frequency it will emit. The color of light is dependent on its wavelength, so this means that the largest nanocrystals will emit red light and the shortest will emit blue, with all the other colors appearing in between. This color-changing phenomenon is the result of different band gaps between different size quantum dots. The band gap of a semiconductor is the energy required for its electrons to enter an excited state. Small dots have large band gaps, so they require a lot of energy to enter an excited state. This high-energy input results in a high-energy frequency, meaning a smaller wavelength of light. This is why smaller dots emit light towards the blue end of the spectrum, and larger dots emit light towards the red end of the spectrum. Quantum dots can be created in a few different ways, but in very simple terms, they are generally made by a chemical reaction in a solution resulting in solid nanocrystals. The chemicals are combined over heat and begin to react around 255 degrees Celsius. The length of the reaction affects the size of the crystals. As soon as the mixture is removed from the heat, the reaction will end and the particles will retain their size and color. Many different semiconductor materials can be used to create quantum dots, such as cadmium selenide, cadmium sulfide, lead selenide, lead sulfide, indium arsenide, and indium phosphide. All of these combinations include heavy metals, which are regulated by the FDA. This makes it difficult and potentially dangerous to market products with quantum dots, and limits the possibility of biological imaging using quantum dot technology. The most promising options so far are copper indium sulfide crystals with a zinc sulfide protective shell. So why am I telling you about quantum dots? Their unique properties are useful in many different applications, from medical imaging, energy-efficient lighting and displays, to photovoltaic cells. Quantum dots will emit light through photoluminescence or electroluminescence. This means that solutions of quantum dots glow when stimulated by ultraviolet light or electricity. Quantum dots are ideal for use in solar cells because they can be synthesized at a variety of different sizes fairly easily. Using many different size semiconductor particles in the photocell means that it will be able to absorb energy from a greater portion of the light spectrum than current photocells. Quantum dots can also be used for vivid, energy-efficient displays and lighting. Some companies are already using quantum dots to provide bright, backlit LCD screens, but soon quantum dot-only displays could be a possibility. These displays can be created in sheets, allowing for flexible screens and vibrant colors. Quantum dots are being used experimentally in medical imaging as highly accurate fluorescent tags. As previously mentioned, quantum dots are created using tiny heavy metal-based crystals. There is significant concern about how these tiny particles of potentially toxic metals will travel, collect, and decay within the body. A study in 2013 concluded without any evidence of toxicity in mice and monkeys, although after 4 months the mice showed an accumulation of particles in the spleen and liver. The monkey's organs did not show any accumulation or side effects, but there is still a lot of research to be done before we see quantum dots become a staple of medical imaging. The commercial demand for quantum dots is expected to grow significantly in the next decade. According to Allied Market Research, we can expect to see demand for quantum dots grow by almost 30% by 2020. Companies and researchers continue to explore the possibilities for quantum dots. These particles are being studied for their possible applications in quantum computing, biosensors, transistors, diode lasers, and battery technologies.